Hello and welcome to Math Zone African Motives. Today we're diving into the fascinating world of relative motion. By the end of this tutorial, you will be able to calculate the relative velocity of objects moving in one dimension. Our main tool for today is the formula for relative velocity, the velocity of object A relative to object B. We can write this as v of AB, which means the velocity of A as observed from B. This formula tells us that the velocity of A relative to B is equal to the velocity of A relative to a stationary reference frame, like the ground, minus the velocity of B relative to that same reference frame. An important concept in relative velocity is that of a stationary frame of reference, often referred to as the ground. This provides a common basis for all velocity measurements in a system. Let's also recall a fundamental kinematic equation that connects displacement, velocity, and time. This is S equals V times t, or displacement equals velocity multiplied by time. The key here is that the displacement s and the velocity v in this equation must be relative to the same reference point, and the displacement must be uniform. Let's start with our first problem, which is question 1 from activity 1. The problem states, a man on a train is walking to the back of a train at a speed of 2 meters per second, while the train is moving forward at 10 meters per second. To solve this, we first need to establish a consistent reference frame. We'll use the ground as our stationary point. Let's define velocities with respect to the ground, which we'll denote with a subscript g. We'll choose the forward direction of the train as positive. Therefore, the train's velocity relative to the ground is positive 10 meters per second because it's moving forward. So the train's velocity is positive 10 meters per second. The man's velocity relative to the train is 2 meters per second in the backward direction. So we'll write this as negative 2 meters per second. The man's velocity relative to the train is negative 2 meters per second. Now let's tackle part A. Part A asks for the man's velocity relative to the train. Based on our established reference frame, we already have this value. The man's velocity relative to the train is simply negative 2 meters per second. The negative sign indicates the direction, which is backwards relative to the train. So, the man is walking at 2 meters per second towards the back of the train. Now for part B. Part B asks for the train's velocity relative to the ground. This is another value we've already defined. The train's velocity relative to the ground is positive 10 meters per second. The positive sign tells us the train is moving forward at a speed of 10 meters per second with respect to a person standing on the ground. Finally, let's solve part C. Part C asks for the man's velocity relative to the ground. This is where we'll use our relative velocity formula. We are looking for v of mg. The formula for the man's velocity relative to the ground is the man's velocity relative to the train plus the train's velocity relative to the ground. Let's substitute our known values into this equation. We have v of mg equals negative 2 meters per second plus 10 meters per second. This gives us a final result of positive 8 meters per second. So, the man's velocity relative to the ground is 8 meters per second. The positive sign means he is moving in the forward direction, even though he's walking backwards on the train. The train's forward speed is so much greater that he's still moving forward overall, just slower than the train. The memo agrees with our answer. The man's velocity relative to the ground is 8 meters per second. Next up is question 2 from activity 1.1, involving a boat in a river. The problem states, a river is flowing due south at 3 meters per second. A motorboat has a maximum velocity of 6 meters per second in still water. First, we set up our reference frame. We'll define north as the positive direction, making south the negative direction. So our reference frame is north is positive, south is negative. Now let's identify our velocities. The river's velocity relative to the ground is south at 3 meters per second. This means the river's velocity, v of rg, is negative 3 meters per second. The boat's maximum velocity in still water is 6 meters per second. Still water is our reference frame for the boat's own engine power. This is the boat's velocity relative to the water. The boat's velocity relative to the water, v of br, can be either positive 6 or negative 6, depending on the direction the boat points. Let's solve part A. Part A asks for the boat's velocity relative to the riverbank when it's moving downstream. Downstream means the boat is moving in the same direction as the river flow, which is south. Since south is negative, the boat's velocity relative to the water is negative 6 meters per second. So v of br is negative 6 meters per second. We need to find the boat's velocity relative to the ground, v of bg. We'll use the relative velocity formula. The formula is v of bg equals v of br plus v of rg. Plugging in our values, we get v of bg equals -6 plus -3, which equals -9 meters per second. This means the boat is moving at 9 meters per second towards the south. Its own speed combines with the river's speed. The memo confirms our calculation. The final velocity is -9 meters per second. Now let's solve Part B. Part B asks for the boat's velocity relative to the riverbank when it's moving upstream. Upstream means the boat is moving against the river's flow. Since the river flows south, upstream is north. North is positive, so the boat's velocity relative to the water is +6 meters per second. 6. So v of ber is +6 meters per second. We use the same relative velocity formula. V of bg equals v of br plus v of rg. This gives us v of bpg equals +6 plus -3, which equals +3 meters per second. The boat is moving at 3 meters per second towards the north. Despite its efforts to go north, the strong south-flowing river slows it down considerably. Again, the memo matches our result. The velocity is +3 meters per second. We've reached question 3. This problem involves two cars moving in opposite directions. The problem states, two motor cars are 1.2 kilometers apart and moving in opposite directions. Car A is moving at 80 kilometers per hour due east, and car B is moving at 100 kilometers per hour due west. Let's set up our reference frame. We'll define east as the positive direction. So our reference frame is east is positive. This means the velocity of car A, v of ag, is +80 kilometers per hour, and the velocity of car B, v of bg, is -100 kilometers per hour because it's moving west. The distance between them is 12 kilometers. Let's begin with Part A. Part A asks for the velocity of car A relative to car B. The formula is v of a b equals v of ag minus v of bg. Substituting the values, we get 80 minus -100, which simplifies to 80 plus 100, giving us 180 kilometers per hour. This means that if a passenger in car B were to look out the window, car A would appear to be rushing towards them at 180 kilometers per hour. Part B asks for the time it takes for the cars to reach each other. They will reach each other when the relative distance between them becomes 0. The speed at which they close that distance is their relative speed. So for Part B, we'll use the relative velocity we just calculated. We have the formula S equals v times t. We can rearrange this to solve for time, t equals s over v. Here, s is the initial distance, 1.2 kilometers, and v is the relative speed, 180 kilometers per hour. Dividing them gives us approximately 0.1006666 hours. The problem is likely expecting an answer in seconds. Let's convert. We multiply the time in hours by 3,600 seconds per hour. This gives us exactly 24 seconds. So the cars will meet 24 seconds after starting. A quick check of the memo shows this matches. The memo also states to 4 seconds. Our answer is correct. Finally, Part C asks for the distance car A travels to reach car B. For Part C, we use the displacement formula for car A. We use the same formula, S equals v times t, but this time we use the velocity of car A with respect to the ground and the time we just calculated. So S equals v of ag times t. That's 80 kilometers per hour times 24 seconds. We can't multiply hours and seconds directly. Let's convert the velocity to meters per second, or the time to hours. The memo suggests converting the time. We can multiply the 4 seconds by the conversion factor 1 hour over 3,600 seconds. This gives us 80 times to 4 divided by 3,600, which is approximately 0.533 kilometers. Converting this to meters, we multiply by 1,000 to get 533.3 meters. The memo confirms this result. Now let's tackle question 4. This one is similar, but the cars are moving in the same direction. The problem says, two cars are 2.2 kilometers apart and moving in the same direction. Car A is at 90 kilometers per hour, and car B is coming from behind at 110 kilometers per hour. Let's assume the direction they are moving is east and set east as our positive direction. Our reference frame is east is positive. So the velocity of car A, v of ag, is +90 kilometers per hour, and the velocity of car B, v of bg, is positive 110 kilometers per hour. The initial separation is 2.2 kilometers. Notice that car B is faster and is behind car A. Let's start with part A. Part A asks for the velocity of car A relative to car B. The formula is V of A B equals V of AG minus V of BG. Plugging in the values, we get 90 minus 110, which equals negative 20 kilometers per hour. The negative sign means that from the perspective of car B, car A is moving backward at 20 kilometers per hour. In other words, B is closing the gap with A at 20 kilometers per hour. The memo confirms this. Our answer is correct. Part B asks for the velocity of car B relative to car A. For part B, we switch the order. The formula is V of BA equals V of BG minus V of AG. Substituting the values, we get 110 minus 90, which equals positive 20 kilometers per hour. The positive sign means that from car A's point of view, car B is moving forward, getting closer at 20 kilometers per hour. Notice that V of AB is just the negative of V of BA. The memo agrees with our calculation. Part C asks for the time it takes for the cars to reach each other. Since car B is faster and is behind A, it will eventually catch up. We need to find the time it takes for car B to cover the 2.2 kilometer gap at the relative speed of 20 kilometers per hour. We use our trusted formula S equals V times T. To be consistent with the memo, let's work in meters and seconds. 2.2 kilometers is 2,200 meters. 20 kilometers per hour is 20 times 1,000 divided by 3,600, which is approximately 556 meters per second, meters per kilometers. The memo does this conversion slightly differently. It starts with T equals S over V and substitutes S as 2,200 and V as 20 times 1,000 over 3,600. This simplifies to 396 seconds. We can convert this to minutes by dividing by 60. 396 divided by 60 is 6.6 minutes. This matches the memo. Now for part D. Part D asks for the distance car A travels to be reached. We use car A's ground velocity and the time we just found. S equals V of AG times T. That's 90 kilometers per hour times 6.6 minutes. To multiply these, we convert minutes to hours by dividing by 60. This gives us 90 times 0.11, which is 9.9 kilometers. The memo confirms this result. And finally, part E. Part E asks for the distance car B travels. We use car B's ground velocity and the same time. S equals V of BG times T. That's 110 kilometers per hour times 6.6 minutes. This gives us 110 times 0.11, which is 12.1 kilometers. The memo again confirms our answer. Question 5 takes us into a mine shaft. Here we have two hoists, A and B. The problem states, in a mine shaft, hoist A descends at 2.2 meters per second and passes hoist B, which is ascending at 3.1 meters per second. Figure 1.1 shows a diagram. The diagram clearly shows hoist A moving down and hoist B moving up. Here's the diagram from the problem. For our reference frame, we'll define up as the positive direction. Our reference frame is up is positive, down is negative. This means the velocity of hoist A, V of AG, is negative 2.2 meters per second. And the velocity of hoist B, V of BG, is positive 3.1 meters per second. Let's solve part A. Part A asks for the velocity of hoist A relative to hoist B. The formula is V of A, B equals V of AG minus V of BG. Substituting the values, we get V of AB equals negative 2.2 minus positive 3.1, which results in negative 5.3 meters per second. From hoist B's point of view, hoist A is approaching it from above at a speed of 5.3 meters per second. The negative sign confirms the downward relative motion. The memo confirms our answer. The velocity of hoist A relative to B is negative 5.3 meters per second. Now for part B. Part B asks for the velocity of hoist B relative to hoist A. The formula is V of BA equals V of BG minus V of AG. Plugging in our values, we get V of BA equals 3.1 minus negative 2.2, which becomes 3.1 plus 2.2, giving us positive 5.3 meters per second. This means that from hoist A's perspective, hoist B is approaching from below at a speed of 5.3 meters per second. The positive sign confirms the upward relative motion. Again, the memo matches our calculation. The velocity of hoist B relative to A is 5.3 meters per second. Question 6 provides us with relative velocity and asks us to find a ground velocity. The problem states, A and B are moving in a straight line towards each other. If the velocity of A relative to B is 7 meters per second, and the velocity of A relative to the ground is 4 meters per second, calculate the velocity of B with respect to the ground. Let's first clarify our signs. The problem says A and B are moving towards each other. If we say A's velocity, v of AG, is positive 4, then v of BG must be negative. So we have v of AG equals positive 4 meters per second, and the relative velocity v of AB is 7 meters per second. We'll use our standard relative velocity formula. The formula is v of AB equals v of AG minus v of BG. This formula is typically derived assuming the g frame is the positive direction for the first object, and the second object is moving against it. However, the signs of the velocities will determine the final direction. Now we substitute the values we know into the equation. So 7 equals 4 minus 5 of BG. Our goal is to solve for v of BG. To do that, we can rearrange the equation. If we add v of BG to both sides and subtract 7 from both sides, we get v of BG equals 4 minus 7, which is negative 3 meters per second. The negative sign here is crucial. It tells us that our initial assumption of A being positive was correct, and B is moving in the negative direction. Let's verify this. If A is moving at plus 4 milsecond and B at 3 milsecond, their relative velocity is 4. 3 equals 7 equals, which matches the problem statement. So the velocity of B with respect to the ground is 3 meters per second in the direction opposite to A's motion. Question 7 is a multi-part problem involving two objects moving in the same direction. The problem states, two objects A and B are moving in a straight line on a horizontal plane in the same direction. B is 12 meters ahead of A and is moving at 4 meters per second. A is moving at 10 meters per second. Let's define their direction of motion as positive. So we'll call that direction positive. This gives us v of AG equals positive 10 meters per second, and v of BG equals positive 4 meters per second. Part A asks for the velocity of A relative to B. For Part A, we calculate v of A to B. The formula is v of AB equals v of AG minus v of BG. Plugging in the values, we get v of AB equals 10 minus 4, which is positive 6 meters per second. This means that from B's point of view, A is approaching it from behind at a speed of 6 meters per second. Part B asks for the time it takes A to catch up with B. For Part B, we'll use the relative displacement and the relative velocity we just calculated. The distance A needs to close is 12 meters, and it does so at a relative speed of 6 meters per second. Using S equals V times T, we get 12 equals 6 times T. Solving for t, we find that t equals 2 seconds. So object A will catch up to object B in 2 seconds. The memo confirms this result. The memo also shows 2 seconds. Our answer is correct. Question 8 is very similar to question 1, but with different values, and the man is walking to the front instead of the back. The problem states, a man on a train walks to the front of a train at a speed of 2 meters per second while the train is moving forward at 15 meters per second. Calculate the man's velocity relative to the ground. Just like before, we'll set up our reference frame. Let's choose the forward direction of the train as positive. The man is walking towards the front, so his velocity relative to the train will be positive. The train's velocity relative to the ground, v of tg, is positive 15 meters per second. The man's velocity relative to the train, v of mt, is positive 2 meters per second. We need to find the man's velocity relative to the ground, v of mg. Using our relative velocity addition formula, v of mg equals v of mit plus v of tg. Plugging in our values, we get v of mg equals 2 plus 15, which is positive 17 meters per second. This means that a person standing on the ground would observe the man moving forward at a total speed of 17 meters per second. He gets a boost from the train's motion. The memo confirms our answer. The man's velocity relative to the ground is 17 meters per second. Our final problem is question 9, which involves an aeroplane and wind. The problem states, An aeroplane can fly at 80 meters per second in calm conditions. A wind is blowing due north at 30 meters per second. Calculate the relative velocity of the airplane with respect to the ground when it is flying. First, let's establish our reference frame. We'll define north as the positive direction. Our reference frame is north is positive, south is negative. The aeroplane's speed in calm conditions is its speed relative to the air, not the ground. The wind's velocity relative to the ground, v of wg, is positive 30 meters per second. Part A asks for the velocity when the aeroplane is flying north. For Part A, the aeroplane is flying north. This means the aeroplane's velocity relative to the wind, v of aw, is positive 80 meters per second. We're looking for its velocity relative to the ground, v of ag. We use the formula 5 of ag equals v of aw plus v of wg. Substituting the values, we get v of ag equals 80 plus 30, which is positive 110 meters per second. The aeroplane's speed relative to the ground is 110 meters per second. The wind is a tailwind, so it increases the plane's ground speed. Part B asks for the velocity when the airplane is flying south. Now, for Part B, the airplane is flying south. Since south is the negative direction, the airplane's velocity relative to the wind, v of aw, is negative 80 meters per second. We use the same relative velocity addition formula, v of ag equals v of aw plus v of wg. Plugging in the values, we get v of ag equals negative 80 plus 30, which is negative 50 meters per second. The airplane's speed relative to the ground is 50 meters per second towards the south. The wind is a headwind in this case, slowing the plane's ground speed. Let's quickly review the core concepts we used today. First, we learned about relative velocity. The velocity of object A relative to object B is the velocity of A relative to the ground minus the velocity of B relative to the ground. This formula lets us see motion from different points of view. A related concept is vector addition. When we have velocities relative to an intermediate reference frame, like a man on a train or a boat in a river, we add the velocities to find the ground velocity. For example, the velocity of the man on the train relative to the ground is his velocity relative to the train plus the velocity of the train relative to the ground. Finally, to relate motion to distance and time, we used the fundamental kinematic equation. Displacement equals velocity times time. Remember, it's critical to be consistent with your reference frames, especially when assigning positive and negative signs for direction. Thank you for watching this tutorial from Math Zone African Motives. If you found it helpful, please subscribe for more math and science tutorials.